Hello everyone, thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Collapse of Frames, and it is going to provide you a broad overview of theorems of plastic analysis and also the analysis of plastic frames. I am going to give you an overview of what I am covering today's video. First at all, we will have a look at some fundamentals of the theorems of plastic analysis, then move on to the plastic analysis of frames, then wrap up with conclusions. Initially, we will introduce the theorems of plastic analysis. It includes lower bound, upper bound theorems, and the uniqueness theorem. For lower bound theorem, if in a structure subject to loading defined by a positive load factor lambda, a bending moment distribution satisfying the equilibrium and yield conditions can be found, then lambda is less than or equal to the collapse load factor lambda c. In this case, the value of lambda is a lower bound to lambda c, that is an estimate which is smaller than lambda c. For upper bound theorem, if in a structure subject to loading defined by a positive load factor lambda, a bending moment distribution satisfying the equilibrium and mechanism conditions can be found, then lambda is greater than or equal to the collapse load factor lambda c, that is an estimate which is larger than lambda c. For uniqueness theorem, if a structure is subject to loading defined by a positive load factor lambda, and a bending moment distribution that satisfies all three conditions can be found, then lambda equal to lambda c. It is impossible to obtain a bending moment distribution at any other load factor that satisfies all three conditions simultaneously. The objective of plastic analysis is to find collapse loads or load factors, like to find a collapse load for this bridge. The hand calculations for this are straightforward, involving ideas about geometry. It is much more important to understand the behavior of the structure as it collapses. In this video, we will introduce the hand calculations for plastic analysis. The first method is the free and reactant bending moment method for finding collapse loads. A beam with fixed ends and carrying a point load is shown in Figure A. This figure shows the bending moment diagram for elastic behavior. The largest moment, W times A times B square over L square, occurs at A. It would be possible to follow through the behavior by inserting a hinge first at A, and then at other points when the bending moment becomes equal to the plastic moment. This process would give a bending moment diagram at collapse and a collapse mechanism, as in Figure E. It is possible to draw the collapse mechanism and the bending moment diagram without any analysis by using two rules. In the first rule, hinges form at restrained ends of beams, points A and B in Figure A. The second rule is that hinges form under point loads, point C, Figure A. Even at the point of collapse, the bending moment diagram is made up from the reactant and free bending moment diagrams. These are shown in Figure F for the fixed beam. The geometry of the bending moment diagram at collapse gives the collapse load, actual bending moment under point load MP, plus reactant bending moment at point load MP equal to WC times A times B over L. That is this WC equation. Now we know how to calculate a fixed beam. Next, we will introduce the analysis of a portal frame. The analysis of a frame must cover other possibilities than just the analysis of a beam. The frame may collapse by being pushed sideways by horizontal forces. An individual beam may fail owing to vertical loads, or there may be some combination of both. The free and reactant bending moment method relies on being able to design the mechanism and bending moment diagram at collapse, which can be more difficult in a frame. The method of determining collapse loads based on the principle of vertical work has proved to be a powerful tool for beams and frames. The method is based on two premises. When a framed structure collapses, or deformation of the structure occurs by rotation at the plastic hinges, the simple supports and internal pin connections. The principle of vertical work can be applied to these deformations. Figure A shows a frame. There are now horizontal and vertical forces acting on the structure. There are various possibilities for the mechanism. In fact, a separate calculation is required for each mechanism. The first case is the beam collapse. In this case, collapse is caused by the action of the vertical force alone. The plastic hinges and imposed rotations are shown in Figure B. The hinge positions follow the previous rules because the ends of the beam are restrained by the connections to the columns. The deflections and rotations can be thought of as vertical displacements, so that we have this equation. The external work done by the applied loads equal to the internal work absorbed by rotation of the plastic hinges. Notice that the tops of the columns are assumed to remain stationary so that the horizontal force does not work. However, the horizontal force doesn't have to be zero. Thus, we have this equation. Next case is the sway collapse. Collapse is caused by the horizontal force alone, and the structure is pushed sideways. The mechanism forms when there are plastic hinges at the top of both columns. The hinges at the feet of the columns are free to rotate and are unable to absorb any work. This sort of hinge is built into the frame and is assumed to be frictionless, so that it offers no resistance to rotation. Since all deformation occurs by hinge rotation, the beam will not change length, and the top of each column moves sideways by the same infinitely small distance. Since the columns are the same length, the hinge rotations are the same in both external and internal work, so that at the collapse we obtain this equation. In this mechanism, the vertical force does not work because the tops of the columns are assumed to move sideways, but not downwards. The third case is combined beam and sway collapse. In fact, it is only significant in the special case when the basic vertical rotation is the same in the beam and sway mechanisms. That is, theta equal to alpha. What happens is shown in this figure. The rotation of the left-hand column and the left-hand end of the beam are such that the members remain at right angles to each other where they connect together. This means that there has been no plastic rotation at that point, so that the plastic hinge and its work-absorbing capacity at the left-hand beam-column intersection is removed from the beam and sway mechanisms. The work equation for the combined collapse mechanism is obtained by adding the work equations for the beam and sway collapse, and then subtracting from the internal work the work done by the hinge which disappears. Thus we have this equation. The concept of combined mechanisms to remove plastic hinges is very important and must be thoroughly understood. Now we ask a question: which is the most likely mechanism? This is a difficult question to answer, because the actual collapse mechanism depends on the relative values of the forces H and V. These equations determine the loads at which the mechanisms form. They can be plotted on a graph with axis V times L over MP, and capital H times H over MP, as shown in this figure, and represent 3 straight lines. The graph is called an interaction diagram. The shaded area, called the permissible region, indicates combinations of V and H that are safe against the collapse by any of the possible mechanisms. If V and H are such that the corresponding point lies on the boundary of the permissible region, then collapse will occur. Suppose the forces are in the ratio V over H equal to 1 over N. Assume that V equal to 1, so that H equal to N. Plot on the interaction diagram the point A. The point at which the line through the origin and A cuts the boundary of the permissible region gives the collapse mechanism, combined as shown, and the values of V and H at collapse, as shown, V equal to 4.75 MP over L and H equal to 1.625 times MP over H. From conclusions what we learned, it has been to specify the important collapse mechanisms, and then to determine the laws that cause the mechanisms. For each mechanism, use the geometry of the mechanism to find the relative magnitudes of the plastic rotations and the distances through which the laws move. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.